Hey, it's Justin, and this is my last minute entry for the Summer of Math Exposition 2022. Um, I have been taking guitar lessons this year, and I never played guitar before. So shout out to my teacher, Andrew, if he's out there listening. Hopefully I won't do him wrong. And anyway, wanted to take this time to not only share music with you, but also to use math to describe some of the concepts that we hear in music, to see if there's a mathematical description. So sometimes when we hear music, and I'll just play you a quick cadence here. Sometimes when we hear a cadence like that, we just think, wow, that's really neat. And we enjoy the aesthetics of it. But we'll begin to explore some ideas here on what makes this so interesting, how to describe it with math in particular. So without further ado, I'm going to go ahead and share some slides and some talking points here. Let's see here. Where is my PowerPoint here? Great. So the first thing you might be familiar with is, in the subject of notes is that we'll cover first is this idea of a pitch standard. When you go see an orchestra, you hear this A, and the idea is that this is what all the other instruments in the orchestra are tuned off of. And the most common note besides this one for tuning purposes are octave intervals. So, and these are usually the doubling of frequencies. And as we'll show in this idea of consonances later on, it's this idea of the waves of sound aligning. It's the best way I can describe it. So within my A, and if I look down at this idea of octaves, I have a really nice clean sound here, and that just reflects the frequency being doubled over every individual octave element. Another idea here between the intervals is this idea of the fifth interval. So sometimes I'll hear an E, and I'll think, what is halfway away from that, and so that'll sometimes be the B here, or that'll be the B here. So in the frequency ratio of these intervals, then if A here is my 440 hertz, then E above is 3:2 ratio of that. That is 660 hertz. So this is the octave. This is exactly double the frequency. And what we describe as sort of halfway in between is that fifth. And so that's just a basic kind of interval. So there is this idea within music called the cycle of fifths. And it begs the question, if I keep on using this 3:2 ratio, what is halfway to halfway? So if this indeed is E at 660 hertz, then could I perhaps go to B here or some other higher note here, and maybe assume that and calculate that to be 990 hertz. And so again, just going by that 3:2 ratio. But if I repeat this through for all the notes, and I kept on going up and down the keyboard, it almost gets me back to, as the notes repeat, back to that integer multiple of 2, but not quite. As you see, the ratio of 3:2 begets a 9:4 ratio, and then if I take 3 and 2 of that ratio against 9:4, I get 27:8, 81:16, etc., etc. In fact, if you can see here, it kind of gets a little bit messy here. If I look at A4 and the relatively notes one octave below and above, as I go through and start calculating against that 3:2 ratio that keeps on changing every fifth, then I go to fourths, I go to eighths, I go to sixteenths, 32nds, and pretty soon I'm increasing my denominator by orders of magnitude of 2. And as I finally iterate back to the A note, I'm almost at exactly 2. I'm at 2.027, which is more likely something over, I guess this is 2 to the 16th power. So in musical history, this idea of just intonation came about, and it was attributed to Pythagoras in antiquity. And the idea here was that for certain musical notes here, I could actually use whole numbers for the intervals. And as you see, it sounds great to be able to have the whole numbers of the intervals laid out in the chords, because it leads to a lot more consonance in the sound itself. But it's not exactly perfect. And when it comes time to adding lots of different instruments or lots of different ranges in the music, it's not perfect. And as I move the octaves up and down in pitch, the consistency isn't maintained. There is also this other idea within musical theory called even temperament. And this is, or even temperament intonation. And if I have my A note being omega, then I could, in theory, just choose, let's see here, what is A? If I choose A and some A below, let's see, I'm still new at the guitar, so I can basically take the different notes between the octaves, the 12 notes between the octaves, and since I'm basically doing a logarithm difference and dividing by 12 different intervals, essentially what I would be taking is multiples of the 12th root of 2 to separate the frequency values of each individual note that is possible between the different octaves. And these individual steps in musical theory, they're actually called demitones. Demitones are are another phrase is called half stepping, where it's possible to, as I progress the music, I essentially, if I were following an even temperament scale, it would be increasing by orders of the 12th root of 2. And if I had used the just temperament, there's a fixed set of whole number ratios that come close, and I have the decimal approximations printed out. But even temperament isn't as perfect. The consonances don't align, and I'll talk a little bit more about what that actually means. So in just temperaments being related to consonances, if I just play a major tonic chord here, where I've got my unison note, the first note, which I'll call sine of x, maybe I'll characterize that as sine, some multiple of sine of x. Then the first major third is sine of 1.25x, or 1 1/4 x. And the next note is that sine over 1 over 5x. And this octave is sine of 2x. And you can hear it has got a really nice clean sound over it. But as you can imagine, in a graph like this just temperament leads to a lot of resonance points. And given the fact that some of these notes are at hundreds of cycles per second, the sine wave, to sort of depict this or describe this, repeats basically every 8 pi. So yeah, that's the idea with just temperament. Now, I could also tune my guitar to have even consonants as well. I mean, I need to have a heck of a precision to be able to do so. And some certain electronic instruments, synthesizers and whatnot, are better capable to handle even temperaments. But there's a lot of art that goes into tuning instruments, depending on the style and what the artist actually likes to have with their particular kind of music. And so the thing is with even temperament, though, is that in this illustration is that there are limitations in how well sonically the notes actually overlap. And because I am not dealing with integers per se and whole numbers for my values of sine of x and the variance thereof, here in this red line here, I've actually got some mismatches that happen. And you might be able to hear it, you might not be able to hear it. I mean, everybody's ears are a little bit different, but from the even temperament perspective, it's a little bit it's a little bit off, and it can manifest itself in many instruments like a jam session or like an orchestra. So I want to talk lastly here about this idea of consonance and dissonance just a little bit more. And so what I'm going to do here is we're going to talk about this octave again. And I'll choose my G note here and the note above. Except I'm going to make that a little bit off. And so now what I'm going to try is this flat ninth interval that includes my first G. But instead of this clean sounding octave above, this is a flat ninth interval. Kind of sounds, well, dissonant. And in fact, if I were to plot out, just what that dissonance actually might look like or be described mathematically, the consonance interval here, what I call the consonance interval, when the waves of sound between this note and the flat ninth interval above actually begin to realign, is actually every 30 pi. And I calculated that basically by understanding or defining the consonants in these waves as, when there's an interval between x and x prime, the consonants might be described as when the sine of x and the sine of x prime is equal to 0, and when the cosine is 1 and the cosine of x prime is greater than 0. So in this regard, it's what we call aligned, or what I call, where the position and the direction are aligned. And so when I try to calculate for the flat ninth here, what that actually meant, I had to think, so the sine of 32 over 15, which is my ratio from the just temperament, n pi, where n is equal to 15 pi, 30 pi, etc., because I need to get it to a whole number. And the cosine, again, where m is equal to 30 pi, 60 pi, where I wanted to be able to get the cosine of the second wave to be greater than 0 and to align. That's how I was able to calculate the consonance interval of this particular flat ninth. So I know this is the first time I have submitted this video, and it's probably my only opportunity for the Summer of Math 2022. But what I wanted to leave you with, and what makes music so interesting, is that it tells a story. And just like math tells a story, so music also tells a story. And consonance and dissonance, are just like questions and answers in math, equations and variables and solutions in math. And that this idea of being able to resolve dissonance in music allows me to be able to tell a story and resolve a story. And it's just like math. There aren't always answers. Not all music resolves. Many music, it just kind of leaves things out in the open. And sometimes math is the same way. So I hope you enjoyed this video. I mean, there's a lot more that I could have covered that I wanted to cover, but given that it's August 15th, I wanted to talk about cadence. I wanted to talk about overtones, why certain instruments actually might sound the same or play the same notes, even though they sound different. Why was that? And there's this idea of overtones that permeate through instruments and even through our own voices. But I'll have to save that for another Summer of Math exposition, maybe 2023. But in the meantime, in 2022, I sure have enjoyed the Summer of Math. And I sure have enjoyed learning how to play guitar. And thanks so much and for sharing this, for taking the time to share this video. And yeah, have a great one. Take care now.